Okay, so we know then that this reduced state of that nicotinamide ring in NADH stores a lot of energy, right? So as I mentioned last time, one mole, that 1 mole of NADH, right, is worth 220 kilojoules per mole of energy, right? And now the question, of course, is why, right? That's what we want to grapple with. Um, so to understand this, right, and ultimately to understand how this synthesis of ATP is going to be powered by those reduced or those high potential electrons stored in that reduced structure of NADH and FADH2, we have to go back to thinking about thermodynamics again. We have to kind of return to where we began, but in a slightly different way, right? We now have to think about the thermodynamics of electron flow, right? Which forces us to think about work or a different kind of work relative to the way we were thinking about it when we started this, which had to do with heat flow. And now we're going to have to think about electron flow. All right, so we start back at the beginning again. We're thinking about thermodynamics. That, of course, brings us back to thinking about, at least in the context that I've written down here, this 220 kilojoules per mole. We know that's source associated with a Gibbs free energy, so a delta G, right? You guys all remember this, which means a good place to start would be to go back to considering, of course, the Gibbs equation, right? And that's the way we sort of have thought about energy and the way in which one would extract useful energy for doing important work, right? Okay, so let's do that. Let's just go back to the Gibbs equation, which just means without thinking about transitions between states, we're going to go back to G, of course, the Gibbs free energy, the work function. G equals H minus Ts, right? You guys all remember that. Okay, but now to incorporate this idea of electrical work into this, we got to approach this in a slightly different way. So I'm going to take a route that we didn't use to begin with. We're going to start with a somewhat more traditional sort of physical chemistry route. We're going to take the Gibbs equation and we're going to start differentiating it, right? And you'll see why in a minute. It's going to look a little ugly when we get to one point, but then we're going to apply some simplifications and life gets much, much easier, right? Okay, so if we differentiate the Gibbs equation, that would look something like this. Differential change in the free energy is just equal to the differential change in the enthalpy, right? Minus, now I gotta do a little product rule application here. Temperature times the differential change in the entropy, right? Minus the entropy times the differential change in the temperature, right? You guys all kind of remember that. Okay, but now we can start doing some substitutions, right? All right, so what do you guys remember, hopefully, about the definition of enthalpy? All right, remember, that's just the internal energy plus the product of the pressure times the volume. And we can differentiate that because that's what we're looking at here. And it's sort of similar sort of thing if we did that, right? The differential change in the enthalpy is just going to be equal to the differential change in the internal energy. And again, application of the derivative product rule, P dV plus V dP, right? Okay, so now putting those ideas together, right, we can now substitute in here and get an expression for the differential change in the Gibbs free energy, which is now going to simply be equal to differential change in the internal energy plus pressure times differential change in volume plus volume times differential change in the pressure, excuse me, minus the temperature times the differential change in the entropy minus entropy times the differential change in the temperature. Okay, that's great. We can do a little bit more substituting here by going back again some of our definitions. Pressure, volume, entropy, temperature, we got handle on all those. That differential change in internal energy, though, that's related to some things, one of which we sort of care about here in a big way, right? Because we started thinking about this question of how do we do useful work based on that energy that's stored in a mole of NADH. So we want to think about work to some extent, right? So that gives us a clue about what to do next. Let's go back to our definition for the first law, which you guys hopefully all remember, which is that energy is conserved. So the differential change in the internal energy is equal simply to the differential change in any heat gained or lost, plus the differential change in any work done on or by the system. Okay, good. So now we can do another substitution here and rewrite our expression here for the differential change in the Gibbs free energy as equal to differential change in any heat gained or lost, plus differential change in any work done on or by our system, plus the pressure times differential change in volume, plus the volume differential change in pressure, TdS minus S dt, right? Okay, that's great. But now we get this big, long, ugly, cascading expression of differentials. Is there anything else we can do? And of course there is. If you remember then back to my definition, and we're gonna think about what we're doing here as being under reversible conditions, which means we can now, if you think back to that definition of the entropy, the classical definition of entropy, as being equal to the differential change in entropy for a reversible process, of course, has to be equal to the differential change in heat gained or lost divided by the temperature, right? Okay, remember, this is formula that equality is only for a reversible process. And we're gonna, I'm not writing the sub ReV down, but for the purposes of this derivation, we're gonna be thinking about this as a reversible process, right? The other constraint we've got here, or the way we've constrained it in the past, was by saying, well, we're only going to allow pressure volume work, right? And if you remember, that meant that the differential change in work was simply equal to this minus P dV, right? If we only allow pressure volume work, that was what the work in the first law was equivalent to. Okay, well, we can rearrange this expression for entropy to say, well, that means that dq has to be equal to ds times t. Well, we can now take those two expressions, both of those expressions, substitute them in, and get a new expression for this big, long differential of the Gibbs work function as dg equals now ds t, or let me write that a different way, TdS minus PdV plus PdV plus VdP minus TdS, oh, come on, minus S dt. Now you hopefully can see what's about to happen here, right? We've now sort of recombined and substituted back in a way that we're going to make some of these terms now go away. We've got minus S dt over here, and we've got T plus TdS here. Okay, that's great. That means I can cancel those guys, right? So those are gone. And then we've got the same thing here with PDV minus PDV plus PDV. Okay, so that's good. So those guys can be canceled. All right, so by and by. So now our expression for this differential form of the Gibbs work function is just dg equal to v dp minus s dt, right? Which is great, right? It's simplifying, but, right, the whole point that we're going through here is we've got to incorporate non-pressure volume types of work. That's where we're headed, right? So that means we need to modify that expression, right? And so to do that, we're going to rewrite this under conditions where we're allowing both pressure volume work and other types of work. The differential change in the Gibbs free energy has to be equal to V dP minus S dt, excuse me, plus dW prime. So that's the differential of any work done on or by the system that is not pressure volume work. Okay. Now, at this point, right, if you're going through a derivation like this, this would be the general expression that would give you the dependence of the Gibbs free energy change on changes in pressure differential changes in pressure, differential changes in temperature, and any additional work. That's sort of will be the general form of sort of a useful derivative of the Gibbs free energy that you could go on to do things with. Okay, but depending on what you wanted to do, you got a fair amount of additional work to do here of differentiating or partial differentiating, working and other things. For our purposes, what we're going to do is we're going to say, well, okay, let's make life simple. And what we're going to do is we're going to say, well, we're going to kind of disallow some things here. We're going to say, let's let the temperature be constant, and let's make sure the volume is constant. And at the same time, let's say the pressure is not going to change. That's like T, V, and P. We're going to clamp those, and we're going to say those are all going to be a constant, right? If that's true, right, then it's fairly easy to see what's going to happen. Well, dP goes away, dt goes away because their temperature and pressure are constant. So those terms go away, which means under those conditions, the expression we now get is that the differential change in the Gibbs free energy is simply equal under these conditions, those constraints, to any non-pressure volume work that's going to happen, right? Or that could happen on or by the system. All right, which is great, because that means if we can approximate at least these conditions here of, you know, sort of something close to reversible or approximately reversible type process, at least in a simple derivation like this, and under conditions where temperature, volume, and pressure approximately don't change, the only thing we need to worry about under those constraints in terms of the Gibbs free energy change is any non-pressure volume work that happens to be done, which is kind of what we care about, which is electrons flowing around, right? All right, so like I said, the kind of work we're going to be caring about, of course, we're going to say, well, let's make W prime, that's equal to sort of electrical work, right? Any work that could be done by the flow of electrons, right? All right, so the next question then is, well, awesome, how do you define that, right? How do you define electrical work? All right, well, how do you define work? If you go back to the classical physics definition of work, right? Work is simply equal to a force, right, applied to an object, right, through some distance, right? And it turns out we can define electrical work in very much the same way. If you imagine a charged particle in an electrical field, right, or more formally, a charged particle that's an infinite distance from some electrical field, right, defined at, you know, whatever way you want to define it spatially, in terms of whether it's circularly symmetric or it's a dipole or whatever. But that charged particle is infinitely far away, right? And we know that that electrical field has some potential density as a function of spatial position relative to whatever's creating the field. The amount of work necessary to take that charged particle from an infinite distance away to a particular point in that electric field, right, multiplied by how charged that particle is, right? Is it weakly charged? Is it highly charged? Is the charge similar to the polarity of that field or opposite to it? Those are the things that would govern how much work it would take to move that particle into that field, or flip it around, at that position in the field and move it to a point infinitely far away, which means it's fairly trivial to show that the simple comparison or derivation you can sort of trivially go through. I'm just gonna write it down, but the form is so similar, it sort of makes some sense based on what I just said, hopefully, that the electrical work is simply equal to, it gets a minus sign for convention reasons, the magnitude of that point in the electrical field where this particle stops, or where you start with it, relative to its movement to an infinite distance away. So the magnitude of the field at that point, right, times Q, however charged it is, right, the amount of electrical charge on the particle. Now, there's a slightly more formal way to write this down, and it goes something like this. We can write this down with a set of parameters that look more, like I said, a little more formally correct, which is minus n times this capital F times this parameter epsilon. Formally, what those numbers are defined as, n literally is the formal charge on this particle that we're thinking about, right? So the formal electrical, I should say formal electrical charge, be a little more correct here, on our particle, right? F then is of course Faraday's constant. And it's equal to 96.4 times 10 to the 3 coulombs, which is one of our fundamental parameters of electrical charge, right? I think it's coulombs. I can't remember the spatial dimension, and my notes have been clipped here, so I should look that back up. It's coulombs. Yeah, I don't recall. All right, in any event, sorry about that. Finally, the epsilon value here is the electric field potential, right, in volts. Right? Okay, so that combination of Faraday's constant, the formal charge, and the electric field potential get you essentially the same thing as, you know, the electric field measured sort of more abstractly, and times the however charged the particle is in a more strictly and quantitative way. That is a simple definition, or is the simple definition of electrical work, right? Okay, now technically, right, what that now lets us say is, well, if that's true, and we had this expression here, right? Well, that's kind of cool, because if I came down here and I said, well, I don't want to just worry about this differential. If I sort of integrated that, right? So the integral of dg is equal to the integral of dw there, or dw prime, right? And I said, oh, well, okay, that means integral here, integral now of the electrical work, right? What that means then is that the transition between two states, like we've been thinking about it thermodynamically, delta G between two states, where we're constant temperature, pressure, we've clamped everything else. The only thing we're allowing, essentially, or the only thing we're considering now is sort of the possibility of electrical work, is simply equal to, now, I dropped a sign here, is simply equal to minus W electrical, which is simply equal to minus N F epsilon, right? Okay. That idea that the amount of the free energy change associated with the movement of electrons, right, or electrical changes of electrical status between two different states is directly connected to a free energy change, is exactly sort of the idea we need to now turn around and figure out where all this free energy in a mole of NADH is coming from. And to do that, we now need to think about a couple of other ideas, which is a really important equation that lets us formally relate those two things and connect it up to an IDM free energy we talked about before, which is sort of, you know, related to chemical potential. We put these two guys together through an equation known as the Nernst equation, and that leads us on to then thinking about electromotive force, right? And that ultimately will help us think about how we can express this free energy that's stored in molecules like NADH. And we'll take that up next time.